Welcome back. Have you ever wondered how we can estimate plane-to-plane transformations and utilize them to create virtual billboards? In the last episode, we talked about this is called homography, but in today's episode, we will demystify how to actually create an algorithm to do this mathematically. Let's dive right in. Just to recap, homography is a projective transformation which essentially mimics a three-dimensional planar transformation between two image planes. So the homography matrix is given as follows, where it has 8 elements and it's in this transformation, lines are invariant, lines remain as lines, the cross ratios are preserved, concurrency is preserved, and collinearity is preserved. So we have 8 number of variables which we need to estimate. So we need 4-point pairs, and just from the previous slides we can use something like a shift feature matching or something like that to essentially like match features between the two images, and just from the previous lecture we can imagine that we have used something like a shift feature detector and we will match 4 points between two image frames. And I'm going to color code the feature points as follows so that we can follow along where they're going. And let's write down the mathematical equations which govern this transformation. So we have our homogenized form of the homography matrix as follows. Let's multiply them together and this is what you would get. And now let's rearrange them by multiplying the denominator to the element on the left hand side, and this is what we would see. We can easily rearrange this and massage this around to make it look like a two-dimensional matrix equation, and this is what it would look like, where we are trying to estimate all the elements from H11 to H32. Remember that we got 2 equations per point pair, but we need to find 8 unknowns, which means that we need 4-point pairs like we discussed before. So if we start like combining them, each element will give you a constraint in the row. For each point you get 2 of these rows and you basically have 8 rows, and we are trying to estimate 8 values H11 to H32. This is of the simple form Ax is equal to b, like in linear algebra, and this is solved using the standard equation, right? And if this is unclear, I would urge you to like subscribe, because I have a future video coming up where I derive this from scratch. Once you know this, you can estimate basically A, and this would work perfectly. This works amazingly well when we assume that there is no noise, and if our feature matching is pretty much perfect, the estimated homography matrix is going to be perfect. Awesome. So how do we do this in the homography era, in the deep learning era? So what we do is we basically feed in 2 images, like the image 1 and image 2, called PA and PB here. We feed it in through a network called a homography net, which essentially predicts an 8x1 vector or a 4x2 vector, depending on how you define it. And then you basically have the ground truth homographies, which is made synthetically by taking images and you are warping with the homography you know, and you essentially train this using a simple L2 loss. And this works out. Of course, there are a little more details. Instead of actually estimating the 8 homography parameters, you would estimate basically what is called the 4-point homography, which is, imagine if you had like the 4 corners of the square in the first image, how would you move them around to make the second image, or vice versa? That's the 4-point homography, and that's what we will use. And this paper called Deep Homography Estimation was written by Daniel DeTone, who is currently at the Facebook Reality Labs and was at Magic Leap before. And Thomas Malisewicz was the other one, who is again in Meta Reality Labs, and Andrew Rabinovich, who works in a company called Headroom, which works on video conferencing. This work was done at Magic Leap. So you can also do this in a completely unsupervised approach, wherein you take the same exact idea, and what you do, the only change you do is you basically say, hey, instead of knowing the exact homography I need, I'm going to warp it and I'm going to make the warped image look like the original image using a simple L1 loss. And W here is the warping function. The warping function is governed by the homography equations we have seen before. And to warp it in a differentiable manner, we use something called a spatial transformer network, and this essentially gives us what we need. The tensor DLT, which you see in blue here, essentially converts your 4-point homography into a full homography matrix in a differentiable manner. Beautiful. So we utilize these concepts of homographies in the deep learning era in dodging dynamic obstacles. This was a work which was done in collaboration with the University of Zurich and ETH Zurich with Professor Davide Scaramuzza's group. So what we did in this case is we coupled the aerial robot to a front and a down-facing event camera, and we were dodging. And this is what dodging looks like. So for the hardware setup, what we did is we had a front-facing event camera which looks at the obstacles. We have a down-facing event camera which is looking at a planar surface in the world, and it is estimating the homography. We utilize this homography to essentially know how much the robot is moved, and we use that to warp the front-facing event camera frames to essentially say, like, we want to find out what is not moving like us. So the first step is we basically denoise the input event frames, which is learned through self-supervised approach, and this is what the output looks like. This is the input, which is noisy and has a lot of dots, and after denoising, it cleans up the dots, and it basically connects all the dots together. We use the down-facing camera's EV homography net like we saw before to estimate the 4-point homography, and then we warp the front-facing event frames using this homography, and we throw this into a EV-seg flow network, which essentially predicts something called segmentation flow. Where it's white, it basically means that it's the background motion, and wherever you see the color, it's the relative motion which we use to dodge the dynamic obstacles. We also wrote a paper on called PRG flow, which was basically to estimate global optical flow for aerial robots across different sizes. So we estimated this thing called the pseudo similarity, which essentially looks like the translation in all three directions in X, Y, and Z, which gives you the scale. So the rotation here is obtained through an inertial measurement unit, which is generally present on an aerial robot, and we could essentially estimate really good ground truth without any filtering. This is just like dead reckoning, right? And we have achieved pretty good results. So here's a table which I wanted to just focus on one thing. The loss function, when we added simple features on the corners and high frequency edges, we actually obtained super good results. And so like all the stuff we've talked about, good features and good corners, when we add that into the loss function, it actually helps us get better results. Another thing which I want to showcase is that when we trained basically on the grayscale images, we trained on the color images, but we actually used the grayscale images. When we trained on the RGB color images and actually did the inference on the grayscale images, we performed better. We speculate that this was because the colors sometimes could get confusing if they changed a lot for the feature matchup, and that was an interesting observation to have. So just to check the understanding, how many degrees of freedom does homography transformation have? How many point pairs do you need to estimate homography? And how do you actually estimate homography? Last question is, how do you make a deep neural network for homography estimation, either supervised or unsupervised? Thank you. See you next time. Take care. Bye-bye.